Every second, nuclear power plants generate enormous amounts of electricity for millions of homes. But unlike coal or natural gas plants, they don't burn fuel. Instead, they unlock the incredible energy hidden inside tiny atoms. Most power plants create heat by burning fuel. Nuclear reactors are different. They generate heat through a carefully controlled process called nuclear fission, producing electricity without burning fossil fuels. The secret lies inside uranium atoms. At the center of each atom is a tiny nucleus containing an enormous amount of stored energy, far more than chemical fuels can provide. When a uranium-235 nucleus absorbs a neutron, it can split into two smaller atoms. This process, called nuclear fission, releases heat and additional neutrons that can continue the reaction. Inside a nuclear reactor, millions of these tiny fission events occur every second. Carefully positioned control rods keep the chain reaction under control, allowing the reactor to produce a steady and safe supply of heat for generating electricity. At the heart of the reactor are fuel assemblies filled with uranium fuel pellets. Although each pellet is only about the size of a fingertip, it contains an extraordinary amount of stored energy. Control rods are the reactor's primary control system. By absorbing neutrons, they regulate the chain reaction and allow operators to safely increase, decrease, or stop power production when needed. The reactor core is enclosed inside a thick steel pressure vessel. This heavy-duty structure safely contains the fuel, coolant, and the controlled fission process occurring inside. Water flowing through the reactor core acts as the primary coolant. Kept under extremely high pressure, it absorbs enormous amounts of heat while remaining in a liquid state. Instead of directly driving the turbine, the hot primary coolant transfers its heat inside a steam generator. This creates high-pressure steam in a separate water loop, keeping the reactor coolant isolated from the turbine system. Inside the steam generator, heat from the reactor transforms water into high-pressure steam. This steam becomes the driving force that powers the entire electricity generation process. The high-pressure steam enters a giant turbine, where it pushes against thousands of carefully shaped blades. As the turbine spins, thermal energy is converted into mechanical energy. The spinning turbine drives a powerful electrical generator. Using electromagnetic induction, the generator converts mechanical rotation into the electricity that powers cities, industries, and homes. Before electricity leaves the power plant, transformers increase its voltage. Higher voltage allows electricity to travel long distance efficiently with lower energy losses. From the reactor core to the power grid, every step works together to deliver reliable electricity. The energy released from tiny uranium atoms ultimately powers millions of everyday lives. Modern nuclear reactors are designed with multiple independent safety barriers. Instead of relying on a single layer of protection, engineers use several robust systems to help contain radioactive materials and protect both workers and the environment. If needed, the reactor can perform a rapid automatic shutdown, known as a scram. Control rods are inserted into the core to absorb neutrons, quickly stopping the sustained fission chain reaction. Even after the chain reaction stops, the reactor continues producing residual heat for some time. That's why emergency cooling systems are designed to remove this heat and keep the fuel at safe temperatures. Surrounding the reactor is the containment building, a massive reinforced concrete and steel structure engineered to provide an additional layer of protection around the reactor and its safety systems. Every moment, operators and automated monitoring systems track thousands of measurements throughout the plant. Together, advanced technology, trained personnel, and multiple safety systems help ensure reliable reactor operation. After several years inside the reactor, fuel assemblies are removed and placed into deep storage pools. The water continuously cools the fuel and provides effective radiation shielding while the fuel's heat gradually decreases. After cooling in storage pools for several years, some used fuel is transferred into dry storage casks. These robust steel and concrete containers are engineered to safely isolate the fuel during long-term storage. Small module reactors, or SMRs, are designed to be more compact than many traditional reactors. Their modular construction can simplify manufacturing and provide flexible options for generating reliable, low-carbon electricity. Researchers around the world are developing next-generation reactor designs that aim to improve efficiency, enhance safety, and expand the ways nuclear energy can support future electricity needs. The future of electricity will likely include a diverse mix of energy sources. Nuclear power can work alongside renewables, helping provide reliable electricity whenever homes, businesses, and essential services need it. As electricity demand continues to grow, many experts see nuclear energy working alongside renewable sources like wind and solar. Together, these technologies can provide reliable, low-carbon electricity around the clock. Today's nuclear power plants use controlled fission to generate electricity. Fusion, which powers the sun, is still being developed for commercial power generation and remains an active area of scientific research. Nuclear technology also plays an important role in space exploration. Compact nuclear power systems can provide dependable electricity for spacecraft and robotic missions operating far from the sun.
Future nuclear plants may increasingly use advanced digital monitoring, robotics, and predictive maintenance to improve efficiency and enhance long-term reliability. AI's flagged Valve 4B for maintenance.
Got it, dispatching a robot. Nuclear reactor is far more than a source of electricity. It's one of the multiple safety engines in Simulations.